So now that we are done with the architecture, let us see how would one train an autoregressive generative model using this particular type of an architecture. Let us look at the training for uh, language modeling or generative models using the transformer architecture. So training using transformers for autoregressive modeling. Okay. Now remember that we are given a sequence of tokens. What we are given is a sequence of tokens. As I said, we'll do assuming that we only have one particular data point, and this can be extended to a data set by putting an outer expectation, as we know. This is x2 up to x capital T, where T is the size of this particular every xt is in vocabulary V. Okay, so what do we want to learn? Remember that in an autoregressive model, we want to learn P of x1, x2 up to xt, and this is modeled as the product from t equal to 1 to capital T, P theta of xt given xt or x less than t, which will, this is the definition of the autoregressive model, right? This is the autoregressive model. Okay, now p theta of xt given t is modeled using, taken to be the output of the transformer at tth token. Training in an unsupervised way is what is called as teacher forcing. For training, here is the idea. Now input token, rather input tokens, is taken to be from x1 x2 till xt minus 1. The last token is discarded, and we take the target tokens, or the target tokens, to be x2 x3 up to xt. Okay, now note that the transformer, because of the masked attention, the transformer is trained to predict xt from xt less than x less than t, which is all tokens prior to xt, right? This is the definition of autoregressive model, right? So if we take our input token to be x1 to xt minus 1, and we take our target tokens to be from x2 up to xt, then what we are implicitly asking the transformer to do is to predict xt from x less than t, which is all x that comes prior to x at t, right? So now how do we define the loss function? Now the loss function L is simply equal to the negative log of t equal to 1 to capital T. We'll take it to be log of y cap computed at t for xt. So just explain what this expression is, where y cap t comma xt is the probability that we have computed for xt given t. So what does this mean? This is actually the output of the transformer at the tth token corresponding to xt, or rather let's say corresponding to the position of xt in the vocabulary V, right? So remember that at each time t, the transformer is going to give a distribution over all the tokens in the vocabulary, right? So we have y cap t comma xt. What is this equal to? This is, or rather y cap t, the way we have defined, is a softmax that we have computed over z tilde, and we know that the sum of all y t's over I equal to 1 to capital V is equal to 1, because we are looking at a softmax. Therefore y cap of t at x t is actually equal to the probability of x t being equal to, okay, let's call it as I here for the sake of ease of understanding. This is equal to xt being equal to the ith token in the vocabulary, given we have seen the history, right? So this is, we can compute this particular loss. This particular loss function is computable via this idea called teacher forcing. What we are trying to do is to minimize the negative of the log likelihood of observing this particular input sequence and modeling it using this autoregressive model using the architecture of transformers. This training is completely unsupervised, and one can actually do it in a supervised manner as well, because let's say that there are pairs of input and target tokens. Here in this case, what we have done is we have taken the input tokens and shifted the input tokens by one place, and we have called that as the target tokens. One can also have a pair of input and output tokens, and the same procedure would apply. But typically for teacher forcing training procedure, we will not need the target tokens. Target tokens are generated in an artificial way via the teacher forcing procedure. This entire training is done in an unsupervised manner. Okay, so let's say that the training is complete. So one last piece of the puzzle is how does one accomplish inference in an autoregressive model? So inference in any autoregressive model. Let us look at how to do that. Now again, one can envisage multiple ways of accomplishing the inference. I'll only discuss one or two famous ways of doing it. The first way to do it is what is called as the greedy decoding. It's pretty simple. As the name says, y capital T star, y cap T star is simply the max of p of x t equal to v less than t, right? So this is over all possible v's that are in the vocabulary. So what we are doing is that, as we saw, right, at every time step, the output of the transformer will be a distribution over all possible tokens in the vocabulary. So you choose that token which would correspond to the maximum. This is p theta star. You choose that particular token corresponding to the maximum value over that softmax that the transformer is giving at every time. So this is called the greedy decoding. Now the advantage of greedy decoding is it's very fast, because you don't have to do anything extra other than just computing this argmax over a vector of length v, so which can be done very fast, and this is deterministic. So every time you fix the input, you get the exact same output at every time using greedy decoding, which can both be an advantage and disadvantage depending upon the application. In an application where you seek deterministic outputs, greedy decoding is the best. But if you seek the output to be, if you are working with an application where output needs to be more quote unquote creative, then it's not a good idea to use greedy decoding, because every time you get the exact same output. The other thing is fully blown sampling based decoding, where the sample yt to be from the categorical distribution or y t cap. So what is happening is, okay, let's call this as y cap star. So what happens is that we get a distribution over the entire vocabulary we know, right? I mean, it's a discrete distribution. Now there are ways to sample from a discrete distribution of size v. Once we get a distribution over there, you just sample from that particular distribution that we have gotten at every time t. So that is how you get the output. Now the advantage here is that this is more diverse compared to the greedy decoding, because every time you are getting different outputs because you are actually sampling. But the disadvantage is that by doing sampling, there need not be coherence in what sort of output that one might observe, right? Unlike in greedy decoding. So there's a mid path that is taken between these two, which is called the top K sampling. Right, as the name says, the idea is to sample only from the top k most probable token. So let vk, which is a subset of the vocabulary, be the top k tokens. How do you define this? Vk is equal to v1 v2 up to vk, where we rank order the probabilities of all these tokens. F v2 greater than or equal to f up to f vk. What we do is first we define a truncated distribution by renormalizing the given distribution. All of these are the output of the transformer P of Vj for Vi is in this truncated vocabulary, and then you sample from the new categorical distribution that is obtained. Okay, categorical distribution of pk. So now what are we doing here? Instead of sampling from the entire distribution here in the naive sampling case, because of possibility of incoherence and so on, what we do is we only take the top k, that k is a hyperparameter, top k occurring tokens, and we find a distribution for those k tokens at every time, and then the sampling is carried out. So now this thing is, if you only, let's say, where instead of choosing all tokens from the vocabulary, we only choose top k of them at every time and then sample from it. So this is one way to reduce the risk of sampling bad tokens and so on. Now there is one other idea which is called an improvisation over this, which is called the top p sampling, also known as the nucleus sampling. It's very similar to top k sampling, but it's sampled from the smallest subset of tokens. Whose total probability mass exceeds some hyperparameter p between 0 and 1. So you choose a probability p, and instead of sampling from top k tokens, you take those tokens, rank order them in such a way that their total probability mass is exceeding the pre-chosen value p, and then sample from that. So that is one way to do it. So this is again, this is adaptive to the context. So what does this mean? Instead of just choosing top k by choosing a k, you make it adaptive in the sense that at every time the number of tokens from which you are sampling is varying depending upon what the context is. So one other way to sample is by temperature scaling. So temperature scaling. Now what is done is, before the linear layer or softmax, okay, just renormalize, call it as z dash of t to be equal to zt divided by capital T, where T is a hyperparameter called the temperature, right? And then we have the usual thing, you have y cap T to be equal to softmax. Instead of softmax of zt, this will be zt dash, which is the scaled version of the logits. Now typically the idea is if t is less than 1, we have sharper distributions, less randomness, and if t is greater than 1, and we have like flatter distributions and so on. This is called the temperature scaling. And if you would have seen in commercially available use cases, transformer based samplers, you would have seen this T as a temperature parameter that is typically used as a user-defined hyperparameter. There are other ways to sample as well. One is the usual beam search, and there is other contrastive decoding and so on. We'll not be looking at those techniques. There are lots of ways to sample or do an inference from an autoregressive model. Okay, so this brings us to the end of autoregressive models and transformers. So this forms the basis for most of the uh, commercially available generative models, such as GPTs. In fact, GPT stands for generative pre-training using transformers. So GPTs and Geminis and Claude and these models, all of them belong to this broad family of autoregressive modeling using transformer as the backbone. Now, from now on, we will look at some of the reinforcement learning based techniques in how to align the autoregressive models that have been trained on large scales of data for a particular preferential data that has been given. We'll specifically look at policy gradient algorithms and algorithms such as PPO, DPO, and so on. That would be the subject matter for the upcoming lectures. Thank you.